Welcome back to ECE 320A. In this video, what we want to do, again, we're in Unit 4, which is dealing with the Laplace transform, and you have homework number 4 due. This is Chapter 12 that we're talking about, and exam number 2 will be at the end of Unit number 5. We want to focus today, or in this video, on the Laplace transform of sinusoids, and we will actually do that by means of using this fundamental building block, which is the Laplace transform of a generic exponential waveform. And this gamma in the exponent is a variable, and we will allow that after we've derived this Laplace transform for an arbitrary gamma, we will replace that gamma with different values, and that will then allow us to create, using Euler's function or Euler's identity, this connection between the Laplace transform of a cosine or the Laplace transform of a sine. Right now, let's just look at this fundamental building block of finding the Laplace transform of e to the gamma t, and then after we've done that, we will let gamma be either real or actually even imaginary, and we'll use that to our advantage to derive the Laplace transform of sinusoids. Now we want to just find the Laplace transform of this exponential, and by definition of the Laplace transform, we have this integral from t equals 0 minus up to infinity. It's the one side of Laplace transform, and we plug in the expression that we want to find the Laplace transform of. There's our function f of t, e to the gamma t. We weight it inside the integrand by this complex exponential, e to the minus st, and we integrate it for all time from 0 minus up to infinity. What we're going to do now, though, is actually play with the property of exponentials, and that allows us now to combine these two exponentials so that now we have e to the minus s minus gamma t, keeping the minus sign out front of the argument, and we had e to the minus st to begin with, so now we have a minus for the gamma t, and that gives us e to the gamma t dt. If we integrate this, remember s and gamma we can simply take as independent variables, independent of the variable of integration t, and we now have this variable minus s minus gamma that is in the argument of the exponent, which then says that the integral of that is 1 over minus s minus gamma times e to the minus s minus gamma t, and we need to evaluate that at t equals 0 minus and t equal infinity. If we do that, then I hope it's clear that if we evaluate that at the upper limit on t, we have e to the minus something dominated by infinity. So now we have e to the minus infinity, which is wiped out or goes to 0 or vanishes. That's what happens at the upper limit. We have nothing. Then we subtract from that the value of this expression at the lower limit, which is then minus, or 1 over minus the quantity s minus gamma, e to the minus s minus gamma, and now we evaluate it at the lower limit, which is 0 minus. Hopefully it's clear now that we have e to the 0, which is 1, and we have these two minus signs that we can combine to actually produce the result that we want, which is the Laplace transform of this exponential, where the exponential was a function of some arbitrary variable gamma, and we're left now with the backside of the bracketed expression is 1. The negatives cancel, and we now have 1 over s minus gamma. That's now the Laplace transform of e to the gamma t. We can now use this fundamental building block of the Laplace transform of an exponential to produce or build or create the Laplace transform of each of these for different values of gamma. For example, suppose we let gamma be a minus positive number, or really now we have a negative number. We now have a decaying exponential as a function of time for our exponential. And if we now replace, if we go back to what we had here, in this particular case, if we replace gamma with minus sigma, I hope that you see then that we have 1 over s plus sigma for the Laplace transform. So here is the Laplace transform of e to the minus sigma t. And if we need to start becoming comfortable with s as a complex number. S is a complex variable, so it has a real part and an imaginary part, and we can now use or evaluate this transform 1 over s plus sigma at different locations in the complex s plane or for different values of s. And in fact, if we evaluate that at a value of s equal to minus sigma, then this particular expression will blow up or become what we call a pole. So if we now evaluated this transformed expression, 1 over s plus sigma, at the location that causes that denominator to vanish, we now have 1 over 0, which is blowing up. That's now called a pole when we find values of s that cause the denominator to vanish, and we indicate those poles with x's in the complex s plane. Summarizing that first row in this table that we're going to produce, we simply see that the Laplace transform of e to the minus sigma t, the Laplace transform of a decaying exponential, you could think of this or try to imagine what this is doing as a function of time. This is now doing something like that. This is now a decaying exponential as a function of time. Its Laplace transform produces this transform 1 over s plus sigma, because we've derived that relationship for the Laplace transform of an exponential. What happens if we now look at the Laplace transform of a complex number or a complex exponential? We now have replaced gamma with j omega. So in this particular result, we simply replace gamma with j omega, and that will now give us the Laplace transform of e to the j omega t, which becomes e to the minus j omega. If we were now to find the value of s that causes the denominator to vanish to produce a pole in the s-plane, that pole would occur at a value of s equal to j omega. This transform 1 over s minus j omega now is going to be vanishing or have a pole when the denominator vanishes, so that that expression itself goes unbounded. And that's going to happen when we move in the complex s-plane right to the position on the imaginary axis equal to s equal to j omega. We're not going to be seeing these e to the j omega t's in a real environment, but we might see them, or we will see those as when they appear in conjugate pairs. So it's nice to now look at what we get for a Laplace transform of the conjugate of e to the j omega t, which is e to the minus j omega t. Or now, if we replace gamma in this earlier result of taking the Laplace transform of an exponential, if we replace gamma with minus j omega, now we end up with 1 over s plus j omega. If we want to know what's the pole associated with that transform, then we're effectively asking what's the value of s that causes the denominator of that ratioed expression to become 0. What value of s causes the denominator to vanish? Well, that's going to happen when s plus j omega is equal to 0, or when s is equal to minus j omega. Again, we will have these occurring in conjugate pairs when we have imaginary exponents, so that we should be seeing whenever we have poles in our system, they will occur in conjugate pairs if they're not purely real. So if we have a pole at j omega, we will have its twin or its cousin at minus j omega. For completeness, let's look at what happens when we have e to the sigma t, where sigma is a positive number. Now we have a growing exponential waveform. We now simply replace sigma with gamma in this expression, and we now have, for a Laplace transform of e to the sigma t, an unbounded exponential waveform in the time domain, gives rise to a transform, or a Laplace transform, of 1 over s minus sigma. To find the pole, we evaluate the denominator or set it equal to 0, and we find that s is equal to plus sigma for the pole of that particular transform. Like I said, that's now our fundamental building block, the Laplace transform of e to the gamma t. We've evaluated that expression, or Laplace transform, for 4 different cases. One where we had a negative exponent, one where we had a positive exponent, that was the first and last row, and 2 cases in the middle where we had imaginary exponents, and that was e to the j omega t and e to the minus j omega t. And those are actually rotating phasors, and they're rotating opposite to each other, which when we combine those together produce sinusoidal waveforms. And we're going to use that to our advantage, because now, instead of having to try to integrate cosine omega t weighted by this complex exponential e to the minus st to find the Laplace transform, we can actually use the linearity property of the Laplace transform together with Euler's identity to rewrite the cosine as this combination, this linear combination of complex exponentials. And that now we already know from rows 2 and 3 of this table what the Laplace transforms of those complex exponentials actually are. Doing that, then let's separate this Laplace transform of cosine omega t into 2 pieces. We can factor out the 1/2 from both terms, and we have 1/2 times the Laplace transform of e to the j omega t plus 1/2 times the Laplace transform of e to the minus j omega t. And we've already found what those Laplace transforms equal. Those are the Laplace transforms in row 2 and row 3 of this table. Or in other words, we now have 1/2 times 1 over s minus j omega plus 1/2 times 1 over s plus j omega. That's not a real clean way of writing the result, so let's now combine these fractions and see if that allows us to end up with a cleaner result. We can push the 1/2 upstairs, and if we combine these or find a common denominator, which will be the product of the two denominators, then we have upstairs in the numerator, we have 1/2 times s plus j omega, and that produces the first term in that two-termed sum, plus 1/2 times s minus j omega, and that produces the second term in that summation in the line above. For the denominator, we now have these four terms. We have s times s, or s squared. We have minus j omega times s. And we also have plus j omega times s, and we have a minus j omega squared. Upstairs, you can hopefully see that we have 1/2 s plus j 1/2 omega plus 1/2 s minus j 1/2 omega. And now we're starting to see things simplify. Downstairs, the imaginary terms cancel, and we have a j squared subtracted from s squared scaled by omega squared, or downstairs we have s squared plus omega squared. That's our denominator. Upstairs, the imaginary terms cancel, and we're left with a 1/2 s plus a 1/2 s, which gives us just s. And that's now the Laplace transform of the cosine omega t. That's now this s over s squared plus omega squared. If we wanted to, we could quickly derive the Laplace transform of a sine. It might be a little bit more tedious because now from Euler we know the sine written in terms of complex exponentials has a denominator of 2j, and the numerator is e to the j omega t minus e to the minus j omega t. Again, this is using Euler. We can now separate that into two terms. And apply rows 2 and 3 of our previous fundamental building blocks. And we now have 1 over 2j times 1 over s minus j omega. That's the Laplace transform of the first e to the j omega piece, minus 1 over 2j. Laplace transform of e to the minus j omega t is 1 over s plus j omega. And now we simply combine these like we did before. We have 1 over 2j times s plus j omega. Again, our denominator is the product of the two denominators, which we know is going to simplify to s squared plus omega squared, and the numerator to complete it is now 1 over 2j with a minus sign multiplying s minus j omega. Again, the denominator is the same as what we had before, so whenever we have a sinusoid with a frequency of omega in sine omega t or cosine omega t, the denominator in the Laplace transform will always be s squared plus omega squared. If you found the values of s that cause that to vanish, they will be at plus and minus j omega. The numerator now is a little different than what we had before. Now I hope you can see that the s terms cancel, and we end up with 1 over 2j times j omega plus 1 over 2j, incorporating the two minus signs, j omega. The j's now cancel, and we can combine the 1/2 omega with the other 1/2 of omega, and we're left now with omega over s squared plus omega squared, and that is the Laplace transform of sine omega t. Or in summary, the Laplace transform of cosine omega t is s over s squared plus omega squared, and the Laplace transform of sine omega t is omega over s squared plus omega squared. And we will be using that and its exponentially damped form throughout the rest of this course, so you need to be very comfortable with that set or pairs of Laplace transforms.